In this video, we're going to be going over application of constraint optimization in economic context or economic phenomena. So in this first question, we have a question. Find the critical values for minimizing the cost of a firm producing two goods, X and Y, when the total cost function is, we have a function here, C is equal to 8x squared minus xy plus 12y squared. And the firm is bound by a contract to produce a minimum combination of goods totaling 42 that is subject to the constraint x plus y equals 42. So we're given a cost function to minimize, and we're also told that as we're minimizing that cost function, the value of goods, the total number of goods x and y that must be produced by that firm should equal to 42. So this is a classical constraint optimization question. So as usual, let's jump straight into it. Okay, so we have our cost function. The cost function is equal to 8x squared minus xy plus 12y squared, subject to the constraint x plus y equals 42. So we have to minimize this function and also take regard that the values of x and y that are going to minimize this function, when they're added, they must equal to 42. So we need to set up our Lagrange function. And if you remember for the last video, our Lagrange function, we can denote it as L is equal to f of x and y, depending on how many variables you have in the original function. In this case, we have only two variables, as x and y, then minus lambda, open bracket, g of x and y, that's the constraint, then minus the constant of the constraint, in this case 42. So, okay, now we can plug in our individual values or the function into this equation. So let's call our own Lagrange function f of x, y, and lambda. That's just going to equal to our initial function that we're trying to minimize here, or we're trying to optimize. That's this function. That's going to be 8x squared minus xy plus 12y squared. Then minus our multiplier, that's lambda, then open bracket. So our constraint function, that's x plus y. So we'll put that here, x plus y, then minus our constant k, that's minus 42. So now let's write our function again. So we have f function of x, y, and lambda, because we have x here, y, and we have lambda. Lambda is another variable in the function. That's equal to 8x squared minus xy plus 12y squared. And let's expand lambda into everything. So we have minus x lambda minus y lambda, then plus 42 lambda. Yeah. So now to get the next step we need to take is we need to take the partial derivatives of with respect to x, y, and lambda respectively. So let's take our partial derivative with respect to x. So we can denote that as f subscript x. So we differentiate everything partially with respect to x. And remember, for the sake of remembrance, that whenever you're differentiating partially, any variable that is not x, or the variable you're differentiating with respect to, in this case x, you treat it as a constant. So it's going to be treated as a normal number. So the derivative of partial derivative of 8x squared with respect to x is just going to be 16x. Partial derivative of xy with respect to x is just going to be y, or rather minus y. Partial derivative of 12y squared with respect to x, since there's no x variable, this whole thing is a number. So the derivative of any number or any constant is equal to 0. So we can write this to be plus 0. The partial derivative of minus x lambda with respect to x is going to be minus lambda. Partial derivative of minus y lambda with respect to lambda is just going to be, with respect to x, sorry, this is going to be 0, so minus 0. And the partial derivative of 42 lambda with respect to x is just going to be 0 too. So the partial derivative of the function with respect to x is just going to be 16x minus y minus lambda. So this is equation 1. Now we'll take the partial derivative with respect to y. Again, we have our function. Now we'll differentiate partially with respect to y. So f subscript y, which means the partial derivative with respect to y, is going to equal to derivative of 8x squared with respect to partial derivative rather of 8x squared with respect to y is just going to be 0, since there's no y variable. The partial derivative of minus xy with respect to y is just going to be minus x. The partial derivative of 12y squared with respect to y is just going to be 24y. The partial derivative of minus x lambda with respect to y is just going to be 0. The partial derivative of minus y lambda with respect to y is just going to be minus lambda. Sorry, this is supposed to be my lambda here. And the partial derivative of 42 lambda with respect to y is just going to be 0. So the partial derivative of the function with respect to y is just going to equal to minus x plus 24y minus lambda. So this is equation 2. And then finally, we need to take the partial derivative with respect to the last variable, lambda. So f subscript lambda, this is going to equal the partial derivative of these three terms here, just going to be 0 since they have no lambda variable. So we can write this as 0. The partial derivative of minus x lambda with respect to lambda is just going to be minus x. And the partial derivative of minus y lambda with respect to lambda is just going to be minus y. And the partial derivative of 42 lambda with respect to lambda is just going to be plus 42. So f subscript lambda is just going to be minus x minus y plus 42. This is our equation 3. So now let's take the next step. And the next step is you set your equation 1, 2, and 3 to equal to 0. And then we'll solve algebraically. Okay, so upon doing that, we're going to have these three functions. So now we can just take lambda to the other side for equation 1 and 2. And then take minus x and minus y to the other side for equation 3. So for this, we're going to have 16x minus y is equal to lambda. That's equation 1. Then we have for this one, minus x plus 24y is also equal to lambda. And for the last one, we have minus x, or rather x plus y is equal to 42. Now, since now that I've gotten to this stage, since we have this to be lambda and this also to be lambda, we can just substitute both of them into each other. So we have, or rather, equate both of them to each other. So we have 16x minus y is equal to minus x plus 24y. So now we can collect like terms. So this will be 16x plus x is equal to 24y plus y. So we're going to have 17x is equal to 25y. So now we can express x in terms of y or y in terms of x, whichever one you choose. So divide both sides by 17. This cancels this. And so x is equal to 25y over 17. And I will have an expression for x. We can now plug that into our constraint x plus y equals to 42 and get our value for y and consequently x. So let's do that. Okay, so now that I'll have this, so we're now going to have this to equal sorry, it's supposed to be a y here. So I have 25 over 17y plus y is equal to 42. So now I can find the LCM of these two. So the LCM of 17 and 1 is just 17. 17 divided by 17, 1 times 25y. That's 25y. 17 divided by 1, 17, then times y, that's plus 17y, and that's equal to 42. So now we'll cross multiply. So we have 25 plus 17, that's 35 plus 7, that's 42. Wow. Okay, yeah, so we have 42y is equal to 42 times 17. So now we can divide both sides by 42. Divide both sides by 42. This cancels this. This cancels this. And so our value for y is equal to 17. Now that we have a value for y, we can now substitute it into the constraint to get our value for x. So that's just going to be x plus 17 is equal to 42. Take 17 to the other side. So x is just going to be 42 minus 17. And x is equal to, 25. X is equal to 25. So x is equal to 25 and y is equal to 17. So these are the values that minimize the cost function. So these are the optimal combination of good x and y that the firm should produce in order to incur the lowest possible cost. So okay, yeah, so we have 42y is equal to 42 times 17. So now we can divide both sides by 42. Divide both sides by 42. This cancels this. This cancels this. And so our value for y is equal to 17. Now that we have a value for y, we can now substitute into the constraint to get our value for x. So that's just going to be x plus 17 is equal to 42. Take 17 to the other side. So x is just going to be 42 minus 17. And x is equal to 25. X is equal to 25. So x is equal to 25 and y is equal to 17. So these are the values that minimize the cost function. So these are the optimal combination of good x and y that the firm should produce in order to incur the lowest possible cost. And finally, we solve for lambda. When x is equal to 25, y is equal to 17, we use our equation 1, that was 16x minus y is equal to lambda. We substitute our values for x and y, and we solve for lambda. That's going to be 16 open bracket 25 minus 17 is equal to lambda. 16 times 25, that's 400, and minus 17 is equal to lambda. 400 minus 17, that's 383. So lambda is equal to 383. So basically, lambda is just telling us that when you have our cost function, I think our cost function was c is equal to I think 8x. Let me find our cost function. So yeah, we have our cost function. This lambda is basically telling us when we plug in our values for x and y into this function, that's x is 25, y is 17, and we get some value. Let's say we get just for the sake of explanation, let's say we get the value to be 6,000. Just hypothetically speaking, this lambda is basically telling you if we increase the constraint. Remember our constraint was x plus y is equal to 42. If we increase the constraint by 1 unit, let's say the constraint increases from 42 to 43, how much is this value of c going to change? And that value is just going to be lambda, or 383. Again, this lambda is basically telling us that when you plug in the values of x and y into the objective function, that's this function here, we're going to get a value. Let's say that value is 6,000, hypothetically speaking. Lambda is basically telling you that when you increase the constraint by 1 unit, the constraint was x plus y equals 42, and you increase that constraint by 1 unit, let's say to like 43, what is this value of c going to change by? And that value is just going to be 693. So when you increase the constraint by 1 unit, this cost function, or our cost, the total cost we're going to incur in numerical value is just going to be 6,383. But if you reduce the constraint by 1, that's from 42 down to 41. Remember, by 1 unit, what is this value going to be? This value is here, 6,000 is just going to reduce by 383, and we see is going to be in turn 5,627, like that. So that's the 5,527, like that. No, yeah, 627. So that's basically the whole concept of lambda. So now we have minimized this cost function subject to the constraint x plus y equals 42. We got our x to be 25. We got our x to be 25, y to be 17, and our lambda to be 383.